Welcome to a video on regression discontinuity that even your Nan and Pop would understand. The aim of this video is to go over what regression discontinuity is in a down-to-earth manner, such that you have an idea what it means and when you encounter it whilst reading some research result. Before I already lost you with the term regression discontinuity, I would like to devote some time to quantification. This is because regression discontinuity depends on quantification. Quantification is simply putting the things we see in our regular life into a number. Some things can be very easy to quantify. Someone's income, for example. We can measure and add up the currency someone receives. Other things, on the other hand, are more difficult to quantify, such as intelligence or ability in a school. Based on how students perform on a test, we obtain a number, and this number is a quantification of the understanding of a student. The main idea of quantification is to allow for large-scale data analysis, where all individuals are measured in a similar format, such that we can compare them to each other and investigate patterns. It allows for grouping in all different kinds, comparisons within classes, between schools, between regions, between countries, etc. This process helps us to standardize objects of study. The next question is occupied with how these numbers can be turned into an improved understanding of the phenomenon at hand. Consider the following graph. It has two axes, with on the x-axis a school score, also can be understood as an average grade, and on the y-axis future income. A single dot represents one person, with a specific combination of score and income. What we can tell from quantification is that there is a possible trend going on. We can link two variables together and observe some kind of connection. As we move along the score variable, we end up with higher values for the income variable. Based on our quantification, we can make some sort of inference for what higher scores predict for income. But before we draw any conclusions, we need to make something very clear. There's a very important distinction between causation and correlation. In the previous graph, we saw a relation: a higher score is associated with higher income. But does that mean someone who obtains a higher income does so because of a higher score, or because there's something else at play? For a more practical example, consider the following figure. Let's say it's dry and hot, sunny summer weather. If we count the ice cream consumption, we can see an increase and simultaneously observe an increase in the number of sunburn incidences. Does this mean eating more ice cream makes you more vulnerable to being sunburned? Probably not, right? There's going to be some underlying factor which is the causal component in this story, namely the current weather. In hot weather, people eat more ice cream, and the additional sun hours lead to more sunburns. We always have to be careful about any statements we make when using data. Is it a correlational statement or a causal one? How do we know what is causal and correlational? This is where regression discontinuity comes in. What exactly does it mean? Regression on its own is a kind of data optimization technique which fits a relation between two variables, possibly taking other variables into account. It tries to fit a line which best predicts the income based on a score level. The discontinuity part refers to a jump in the data. Discontinuity, something stops being continuous. Let's have a look at the previous example. This time we fitted a regression through all the data points, a line that best fits the data. Let's now consider a situation where a government offers a grant. If students score an average grade of 7 or higher, the government is interested in assessing whether the grant influences future income in some way. In the absence of any treatment, this line is just an upward slope, as we can see in the picture. After the treatment, our data gives us the following graph. Can we simply make a comparison between those who received the grant and those who did not to figure out the effect? No. Those with a lower score are inherently different from those with a higher score, for example, more motivated or their parents are better educated. It is hard to know whether differences in the outcome exist because of the inherent differences or because of the treatment, and if both, in which magnitudes. But what regression discontinuity does, it looks at individuals who are slightly above and who are slightly below the score of 7. 7 is our cutoff and where discontinuity or jump occurs. The fact that rules can be discretionary ensures that groups close to the threshold can be very similar except for treatment. Consider these two groups within a range of 6 to 8. These groups, on average, should have similar income, education, motivation, etc. Only the right group can take up the grant, whereas the left group is excluded. The difference between the average incomes between these two groups, the regression discontinuity estimate, can hence be associated with their reception of the grant. This whole idea holds in case of continuity. People on one side of the cutoff truly are similar to those on the other side. This means there is no systematic potential for manipulating yourself into the treatment group. Let's take a quick detour to robustness. As we previously touched upon, certain things need to be valid for the regression discontinuity estimate to really produce a treatment effect. Originally, robustness focused on things in the modeling space. What is the correct modeling and how robust is the most plausible model to other assumptions? Small differences in the measured effect using other assumptions increases our confidence in the original model. Robustness testing in regression discontinuity investigates the strength of these assumptions, no manipulation. But there is more to it than just the identification assumption of continuity. I attempted to show three model space choices that also play an important role in finding an effect of a policy using regression discontinuity. The first one is related to nonlinearity. The relation between a running variable and the outcome need not be linear. This means not every increase in the score will have the same effect on income. Moving from a score of 3 to 4 predicts an increase of 10,000 in income, while scoring 9 instead of 8 leads to a 50,000 increase in income. If this is the case, you need to adjust for it during the estimation procedure. Inability to do so leads to bias in the treatment estimate. Regression discontinuity has the approach to reduce the range of people in the sample, such that the function is approximately linear. Under the assumption of approximate linearity, a single-order polynomial can be used. Higher-order polynomial, in other words a more non-linear model, allegedly have a bad approximation at the cutoff. However, the results show us that higher-order polynomials not necessarily have a bad approximation. What they do have is inefficiency. Whenever the linear approximation was correct, higher-order polynomials will produce similar treatment effects, only with a larger standard error, it being less efficient. And this knowledge can be used as a robustness test when it comes to validifying a linear approximation. The second topic is heterogeneity. Regression discontinuity regressions estimate a treatment effect, but specifically a treatment effect at the cutoff. Besides how the treatment would differ at other points than the cutoff, it could also be the case that different groups are affected in different ways at the cutoff. Simply put, people respond differently, and it is of use from a policy research perspective to figure out the underlying differences so we can correctly implement policy interventions and other kinds of modifications to the causal mechanism. The results provide a framework to think of how an average treatment effect in a regression discontinuity estimator comes about, specifically in terms of how cases are distributed along the score variable density and what differences there can be in the strength of the treatment effect. Finally, spatial dependencies play a role. Many regression models assume every observation in their sample is independent and unrelated to any of the others. But humans interact with each other. Spatial dependencies are the outcome of these interactions. Other people may be influenced by the treatment condition of others. Spillovers refer to people in the control group interacting with those in the treatment group. This influences the measured treatment effect. Synergies refer to interaction between people in the treatment group, which leads to an enhanced treatment effect. In regression discontinuity, we look at people who are very close to each other in some dimension. Chances are that people are also likely similar in other dimensions. In fact, we're trying to find people who are as similar as possible such that continuity holds. If that is the case, it also becomes more likely those people are in contact with each other, increasing the possibility of spatial dependencies. Results from the simulations imply spatial dependencies indeed can play a substantial role in regression discontinuity estimation. Moreover, the only way to deal with spatial dependencies is through modeling them with some form of interaction matrix. Combining knowledge of interaction patterns with the original regression discontinuity approach performs best when it comes to bias and efficiency. So, bring everything together. What have we learned? Beyond the implications for individual model choices, the simulations stress the need for additional robustness tests in regression discontinuity analysis. Naturally, every study needs to consider the potentiality of each threat individually. The argument, however, is that the nature of social science research allows for the presence of each to some degree. Completely ignoring them would be nonsensical. Consequently, the contribution of this paper is a suggestion for future regression discontinuity studies to devote attention to traditional model misspecifications, either in the form of theoretical discussion or, preferably, with the inclusion of robustness tests specified to the model choice.